Pictured below is a graph of an alternating voltage source. We'd like to find the period of oscillation. So one approach we have to finding the period is marking one point when the graph is in one phase and then marking another point when it comes back to that same phase. Since our axes are time in seconds, then this distance here is going to be the period t. Alright, so it looks like the axes are marked every 0.02 seconds. So that makes this 0.04. And then on the other side we have 0.34. So the period will be 0.34 minus 0.04. The period is 0.3 seconds. To find the frequency of oscillation, we'll use the formula F equals 1 over the period. It's 3.33 hertz. Now let's find the maximum voltage, the peak voltage. To get that, we'll simply want the amplitude of the waveform, which looks like 4 volts. Now we're asked to find the RMS voltage, the root mean square, which is like an average of the voltage. It has this formula. And this is the formula for a sine wave. Different waveforms will have different formulas. But let's go ahead and plug in our peak voltage. Divide by the square root of 2. And we get approximately 2.83 volts. So if we were to plot that RMS voltage, it would be right around here. It's a nice visual way to show the difference between the peak voltage and that average RMS voltage. Next, we'd like to come up with a formula for this graph shown. And we're going to need several things. Our voltage as a function of time is going to be V peak times sine of omega t, and in this case we do have a phase shift. So we're going to need to find all those things. The peak voltage, the omega, and the phase difference. The omega will be given by 2 pi f. So that's going to be 2 pi times 3.33 hertz. And now we need our phase difference. Now that's a little bit tougher to find. Well, keep in mind that the phase difference is equal to omega times h, where h is the horizontal shift of the graph. So can we find the horizontal shift of this graph? Well, this is a point where the phase is 0. So if we can just figure out what is the shift that has occurred here. Let's find that horizontal distance in seconds. We call it h. H is approximately 0.263 or so. But that alone is not an angle yet. To turn it into an angle, we want to multiply it by omega. So our phase difference will be 2 pi f times h, which is 2 times pi times 3.33 times 0.263, and this will actually be in radians. Let's see what we get. All right, I get 5.5 radians. Now we can finally write our final answer. All right, we have just about everything we need to construct the function. The omega was 20.9 radians per second. We'll need that number. Let's go ahead and plug in now. We'll get V of t is equal to the peak voltage, which was 4 volts, times the sine of omega times t minus our phase difference that we calculated. All right, we just want to check this now with Desmos.com. And we'll just verify that the function we created does accurately depict the graph that's shown. Okay, we want 4 sine of 20.9 t minus 5.5. All right, we're looking for a graph that has a height of 4. It starts off around 2.8. Yep. And it has a period of 0.3. Yeah, it looks like our period here is about 0.3, so it looks good. Next it says, assume the source is connected to a light bulb of resistance 25 ohms. What could be a formula for instantaneous current when we have a circuit of just a resistor and an AC source like this? Then the formula that we'll have relating voltage and current will simply be Ohm's law. V equals I times R in this case. It's not always that way when it comes to AC circuits. We'll see in the future that it gets a little bit more complicated when we introduce capacitors and things called inductors into the circuit as well. But for just a simple AC source and resistor, we have the formula V equals IR. So the resistance here is just going to be a constant, and our current will have the same basic shape as the voltage. All right, the formula we're looking for now is I of t equals I max sine of omega t minus the phase difference. And we really have everything we need here except for the max current. So let's adapt our formula to deal with the maximum quantities. Now we can plug in our maximum voltage, 4 volts, and plug in our R of 25 ohms. And then we can find the I max. It's 0.16 amps. That's everything we need in order to write the current formula. So as a function of time, current will be given by 0.16 amps times the sine of 20.9 t minus 5.5. Let's plot this within Desmos and see how the current versus time and voltage versus time graphs compare. As we can see, when the voltage is at its peak value of 4, the current reaches its peak value of 0.16 amps. We also see that when the voltage becomes 0, the current becomes 0. And if we go to the maximum voltage in the negative direction, it's negative 4 volts. And our current in the negative direction becomes negative 0.16. So basically, when we have just a resistor and a source, the current and the voltage will be in sync or in phase.